Constant Velocity by James Ashbaugh. As a general introduction, in this lab I analyze data and video observing an object moving with a constant velocity. Furthermore, the purpose of this lab is to understand how to properly implement computational models to simulate movement of an object at constant velocity. Some underlying physics principles include that when an object is moving with a constant velocity, the net force on the object is zero, therefore no acceleration. This is demonstrated mathematically by the image on the right. Also, through using the velocity update formula, we can see that v final equals v initial because the net force is zero. Again, on the right, we can see how this mathematically plays out using our known formulas. In a small preview of my results, I discovered that the model accurately matched my own recorded data from the tracker software. The position versus time graph for both the computer model and the tracker graph matched closely. There were slight deviations arising from sources of error. The image on the right is a snapshot of the middle of my tracker simulation, in which my object of focus is a water bottle, and this represents the system. Everything else surrounding the water bottle represents the surroundings of the experiment. The bottle moves left across the image with a constant initial velocity, and the net force acting on the water bottle is zero. This snippet of code demonstrates the iteration component. Each time step, a new position and velocity is calculated. Velocity remains the same throughout because the net force is zero. Furthermore, these graphs on the right show the output from running the code in the previous slide. Specifically, the bottom right graph shows that the velocity is constant, meaning no net force, throughout the simulation. The graph on the right shows my findings. The predicted data from the computational model and observed data match closely. Both show a positive trend, and sources of error can account for deviations. Going into some possible sources of error, other forces such as friction could have caused the object to experience decreased velocity over time. Air resistance, which causes a slight decrease in velocity over time as well, that is also possible. Also, recording errors could have occurred, such as possible misclicks on the tracker analysis when analyzing it, or not adjusting frames correctly at the beginning and end of the video, which would cause data to experience fluctuations in the beginning of recording. If the orientation of the axes were flipped, instead of a positive sloping position versus time graph, there would be a line with a negative slope. This is because the positive x direction becomes the negative x direction, and vice versa, flipping the axes. The tracker graph on the right would show a negative slope, with the position moving closer and closer to zero over time. Find how many forces are actually acting on the water bottle. We can construct a free body diagram analyzing the water bottle to determine how many forces are acting on it. There is a normal force exerted in the positive y direction, and there is a gravitational force exerted in the negative y direction. These forces are equal and opposite, therefore the net force is zero. The calculations on the right accurately show the vector addition and that the net force on the water bottle is zero. In conclusion, an object moving at a constant velocity has no net force acting on it. The object's motion can be predicted using computer models, and these can help us better understand natural phenomena. Thank you.